Nice to have you back. So let me talk a little bit about the background here, just in case you're not familiar with it. I will start with the physics, then I will talk about the mathematics, and lastly, I will spend some time to connect what we've just learned to what is on the poster. So this is the Fermi surface, and I would like to just dedicate a little bit of time to make a connection to the Fermi surface. So here's our familiar figure again. And if we ask ourselves the question, okay, what is a metal? Then typically the simplest description, the simplest phenomenological description is in terms of Ohm's law. And for Ohm's law, current and voltage are proportional to one another, not just in size, but also in direction. So here you would have that the current I is equal to the conductivity times U. So the conductivity is nothing but the inverse of the resistance. And in general, this is a tensor. So here, in the simplest case, it's just proportional to the identity, but it is, in general, a tensor. And then the distinction between metal and insulator is simply as follows. If the conductivity is, to good approximation, 0, we are dealing with an insulator. If the conductivity is non-zero, then we're dealing with a metal. If you really get into the nitty-gritty, of course, there are different types of conductors, but just let's say to unburden my speech a little bit, I will use conductor and metal interchangeably here. And the big question now is whether or not we can predict whether a material is conducting or not from a microscopic model. And secondly, when exactly is Ohm's law valid? As I said in my introductory lecture, it is better to work with the current density rather than the current itself. And that is because the current scales with the volume. And here we again have a very, very simple relationship between the current density, or to be extremely precise, the expected current density, and the applied electric field. So to emphasize that we're dealing with vectorial quantities, and to distinguish the electric field from the energy, which is always a bit of a pain unless you're using tech where you could make the electric field bold, I'm putting arrows on top. So this makes sense if sigma is a tensor, because, or let's say a matrix, a d by d matrix, because on the right you have matrix, a d by d matrix times a d vector, which gives you a d vector. And of course, in general, this is only true up to an error. So establishing equations like this is usually done with linear response theory. And linear response theory, the idea is deceptively simple. You're saying that, okay, this current depends on the electric field, and I'm just doing a Taylor expansion. So of course I get a 0th order term, which is typically 0. Then I get the linear term, which is the one above. And in principle, I could also derive higher order terms, or I could just say this is small o, so I have to be careful to distinguish this from the sigma. In the electric field. So this is what you can do with rigorous linear response theory. This is not the approach I will take here. This is just to put it into context and connect what I'm saying here to the talks of some of the other participants. So importantly, the conductivity tensor depends on external parameters. For example, the magnetic field B, the temperature, but you can also think of other external parameters. And this is, in fact, what I meant by saying that the magnetic field and the electric field are not treated on the same footing. So in the framework of linear response theory, you only expand in terms of the electric field, but you do not expand in terms of the magnetic field. And that is because they play different roles. Namely, the electric field the purpose is to drive the system out of equilibrium. And in contrast, the control parameters their purpose is to either change the state and or the material properties of the solid that we're describing. So one of the things that I emphasized initially is that we would like to start with a microscopic model. So let's do something really, really simple and take a sample of choice or two and zoom in. Just use an electron microscope, perhaps. And what you would typically see are signs of long-range order. So here you have two different crystalline solids. One is boron nitride on the left. So you see this honeycomb. Okay, this is a very ugly honeycomb that I'm drawing here. Here you have a honeycomb lattice. And on the right, you have gold. So in both cases, you see that these are arranged very, very regularly. And of course, in realistic samples, there may be defects or maybe irregularities, but to leading order, mathematically speaking, you have a translational symmetry. There are, of course, materials that do not have such a rigid crystal structure. So, for example, glasses or other amorphous materials, but these fall outside of the semi-classical description. So here you would have to use the theory of random operators, and this is covered in the mini course by Christian Saldel. So this is not something I will do here. So I will only treat materials that have, at least to good approximation, a nice crystalline structure. And I will use this idealization. So as I said, amorphous materials are possible to treat rigorously, but this is a different mini course. There's also something that we can already infer here. And that is, and that's why I chose these pictures here, there is a spatial scale involved. So 1 nanometer is 10 to the minus 9 meters. And you see that, let's say these, and 1 angstrom is a tenth of a nanometer, so it's 10 to the minus 10 meters. So the typical scale is, of course, not completely independent of the material that you're using, but let's say you are working in the range of 1 to 10 angstroms. So typically lattice distances are between 3 and 10 angstrom. And the point that I would like to make here is that this time scale, this spatial scale, is what requires you to use quantum mechanics. So this is why the microscopic model that we have to start with is a quantum model necessarily. Now, if we zoom out, and let me just remind you that this here is a macroscopic sample. So you can imagine that you're, let's say you have a sample size of, let it be millimeters, but even tens of micrometers. This is very, very large on the atomic scale. So if we want to make this rigorous, then in the experiment, we are always working with a two-scale system. So the green bit here, think of these as the potentials due to the external fields. So here with external fields, I of course mean the electric field and the magnetic field. And these vary on a much, much bigger spatial scale. And then the other scale that you're looking at here, let's say, let's grab one period. This is the microscopic scale. And we already saw that the microscopic scale varies on the order of a few angstroms. And this here, if you think of an experiment, like I said, the fields will vary on a much, much, much larger scale. And that means that the semi-classical parameter in this case is just the ratio of the microscopic to the macroscopic spatial scale. And one very, very, very important fact is that this parameter is not just small, but it is also dimensionless. And this is absolutely crucial, because very often in physics, h bar is taken to be the small parameter, but h bar has units. So I can choose units where h bar is very small. I can choose units so that h bar is 1, or I can choose units so that h bar is 10 to the 80. And that's why quantities with units are not good parameters to characterize physical systems. But here I'm taking the ratio of two length scales, and that means that inherently this quantity here, epsilon, is dimensionless. Why do I call this semi-classical parameter? Well, if epsilon is small, under certain additional conditions, you will see that indeed the semi-classical approximation is valid when epsilon is small, and the error can be quantified in powers of epsilon. But this will come out at the end. So the justification why we can call epsilon the semi-classical parameter, this comes out at the end. For now, if you don't believe that, or if it's not clear, at the very least, I've established that epsilon is a small dimensionless parameter. And you can study expansions of various quantities in epsilon. So there is also something else that is implicit in the picture, and that will become clear in the next section, in section 3, and that is that the microscopic potential need not be smooth, whereas the macroscopic potential looks very smooth and regular. This is not a coincidence, because it turns out that you do not need to make any smoothness assumptions on the periodic potential. So this red thing here is the scale of the periodic potential. I should have said this. And this need not be smooth in any way. But the external fields and potentials have to be. So the last thing that we need, that is important, is the existence of a characteristic energy. That is the so-called Fermi energy. I will denote it with EF. And this here, the Fermi energy determines the state, or is one of the factors that determines the state, for example, together with the temperature. And you can change it to some degree by applying an external potential. So if you apply a voltage difference across the sample, then the Fermi energy will be shifted relative to let's say the natural Fermi energy due to you applying a voltage difference. So lastly, let me also say something about, or let's say raise at least some of the idealizations that we will have to make. And I will, this is just a summary. I will explain the necessity in more detail later on as time goes by. But I think this is a very, very important subject, because in physics, there are, of course, more complicated models that you can choose, but usually the problem is that not all of the interactions are actually important to understand certain effects and certain phenomena. So what you do is you make idealizations. So one of them is that instead of working with a finite sample, you typically work with infinite samples. The idea is simply that the sample is so big that on the microscopic times, if you measure everything in microscopic units, it's so ridiculously big that the size and shape does not matter. So here you neglect finite size effects. The second thing is, and this was something that I already anticipated, is that we will also neglect disorder. And that is because the semi-classical approximation, the way I'm going to introduce it to you here, breaks down when you have an appreciable amount of disorder. So instead, you would have to use different tools. And the third thing I'm neglecting here are electron-electron interactions. So this is known as the single electron approximation. That means that the periodic potential it's not just due to the nuclei, but also due to all other electrons. So these are the idealizations that I'm going to make for the rest of the course. If you want to include electron-electron approximations, then again, we have a mini course where this is covered specifically, but this will not be covered in my mini course here, because also then you don't have a semi-classical approximation in the way that I'm presenting it here. Okay, with that, that's the background on physics. In the next video, I will talk about the how to model systems like this mathematically.